So this lecture is over section 5.2. I'm pulling up the notes right now. All right, I'm gonna be really honest. This section is a little bit tricky and a little tedious. So I'm gonna do my best to make it make sense. Just know that this has a point and we're going somewhere with it, and we'll see more so with that with the next unit. So first, this is a review of sigma notation. This notation means we're going to sum up all the terms of AI from I equals 1 to n. So it's just a shorthand of writing. This would be A1 plus A2 plus A3 plus all the way till we get to A sub n. So find the sum by adding each term together. And then it says we're going from j equals 2 to 5, 1 over 2j. So just trying to see, do you understand what we're doing? So j equals 2 to begin with. So 2 over 2 plus 1 over 2 times 3. We're counting by integers. So 2, 3, 4, and then j is 5. We're going to sum all those up, and we get 77 over 120. All right. Now you can do that in your calculator if you have a TI-84. Let me see if I can share that with you. Okay, so if we do math, where did I get to? Math. Come on, guy. Well, I was going to show you how I typed this in, but you see I summed it up and I got this value, which should be 77 over 120. We can double check. Just taking a second. It's thinking. Oh. All right, I don't really know why it's taking so long. Here, we'll try to do that in a little bit. I don't want to waste your time doing that forever. Hold on, if I load it again, let's see if it decides to work. Share. Yeah, it's still stuck. Well, I should try that later. Sorry about that. Okay, so let's keep going. Use sigma notation. So now this is going backwards. Can we go backwards and write what this would be using the summation? So this would be from I equals, let's see what's I. What's changing here? We have 1 and 2, and then we have 2 and 2. So it looks like the 2 is staying constant. And what is changing is this number in front, which is I, and we start at 1 and we end at 5. So 1 to 5. And then we have to write what the formula is. What are we summing up? 1 over, that's what's changing, that's your I, plus, this is not changing, 2. And then these are summation formulas. They are ways to find formulas to solve for. If you're summing up C n times, it's just C times n. If you're summing up I n times, it's this formula here, which was a proof for it, but I'm not going to worry about doing the proofs with y'all today. This is like if you're summing 1, 2, plus 3, plus 4, plus dot, 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 dot. It's the same thing as doing n times n plus 1 divided by 2. That's how you sum up all those numbers from 1 to n. If you're doing I squared, it's this formula, and I cubed is this formula, which we will use. Okay, so use the properties of summation to figure out what this is equal to. So what we're going to do here is we're going to split it up. So we can split up the summation. The summation of a difference is the difference of the summation. So we can say that this is the same thing as adding up 5i and then doing minus the sum of 4. Okay, from I equals 1 to 16. Now what you can do is you can put these scalar multiples in front, okay? So this is like 5 summation of I minus 4 summation of 1. So what do we do now? Well, how do I solve for I? And we're going from I equals 1 to 16. So remember, it's n times n plus 1. So 16 plus 1 would be 17 over 2. Minus, we're going from I equals 1 to 16. That would just be 16. So we have 4 times 16, because that's where it's just Cn. And so if I do this, I get 616. Okay, if we do this one, first I would say multiply this out. So the first term squared is 4i squared, plus multiply these two and double them. So 2i times 1 is 2i times 2 is 4i plus 1. And then we're going to break apart this summation. We're going to say, and we can pull out the scalar multiples. So it's 4i squared plus 4i plus 1. And we're going from I equals 1 to 22, I believe, for all of these. So I again is n, this 4 gets multiplied, n is 22, n plus 1 divided by 2. Whoops, oh no, that was I squared. I wrote the wrong thing. Sorry, guys. Gotta be careful when you're copying. I squared has a different formula. I squared is n plus 1, 2n plus 1 over 6. And then we have I, which was the n times n plus 1 over 2. And then this is just this times that, 22 times 1, so 22. When you add all that up in a calculator, you get 16,214. So that's just kind of practicing these summation formulas. All right, area under the curve. This is what the integral, which we're talking about in this unit, is going to have its application in. It gives us the area under the curve, which is why we're kind of talking about that here. So if we have an area under a line, that would be easy. It would just be a rectangle. So height times width. But we have area under a curve that's not linear. It's tricky because I could use this height, or I could use the height from over here, but I'm going to have big error. I'm going to have, if I say that this is my area, I get this whole area. So I'm counting a lot that's not there. Or if I do the left-hand side, I'm counting out, I'm not counting a lot of the area that's there. So you can use more rectangles to get a more accurate assumption of the area. And so this is explaining, if we want to estimate the area, what we can do is we can divide this by some delta. So let's say we use delta x as 1. So every 1 unit, I'm going to draw a rectangle. Now I have to get the height of that rectangle, and the height is either going to come by the left endpoint or by the right endpoint. And so it's either going to be an underestimate or an overestimate. And these widths that I'm going over, we're going to call a change in x. So each width is called delta x. And then when you get that delta x, is you take b minus a divided by n. So in this case, if this is 1, 2, 3, 4, that's 4. And I wanted to have 3 rectangles. So n is 3. My width of each rectangle with delta x would be 4 minus 1. That's this distance here, divided by however many rectangles I wanted. So this is 3 over 3. So it shows you that my width is 1, or I'm counting by 1s, which is what I did here. So the area of each rectangle is going to be the f of x value. So that's the y value here, times the delta x. That gives you the area of each individual rectangle. And then you're going to sum all that up to get the total area. So now it says we're going to try to use left and right hand endpoints to figure out what the area is under this curve. So if I'm using 4 rectangles, I'm going to say delta x is equal to b minus a divided by n. So 2 minus 0 divided by how many rectangles? 4. So the width of each rectangle is 2/4 or 1/2. So that means I'm starting at 0 and I'm counting by a half and I'm going to end at 2. So if I count by a half and then I count by another half, that put me at 1, and then another half that put me at 1.5 or 3/2. I like to go back and count my subintervals or my rectangles to make sure I did it right. So look, how many do I have? 1, 2, 3, 4. Did I say 4? Yes. So we divided it correctly. Now, to do left hand, what that means is you're going to take your width in this case is 1/2 times all of them, it's the comma width. But the left hand means you're going to use the left endpoints, and you need to get the y values from here. So to get the y values, you take this and you plug it back into this function. And so it's f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. And for the left hand, you're going to use all of these. You're going to leave out the right one because you only can use 4 because you only have 4 rectangles. You're drawing your heights over like this from the left. Okay, so your left hand rectangles look like that. So if I put that on my calculator, you should get 9. Because it's 1/2 times 1 plus 2 plus 5 plus 10, and we get 9. Now, if I do my right hand, the width is still 1/2, but instead I leave out this one and I use these guys. Now you're drawing your rectangles over this way to find your heights, to find your areas. So f of 1/2 plus f of 1 plus f of 3/2 plus f of 2. If it's an increasing function, this is going to be an overestimate. So 1/2 f of 1/2 is 2 plus 5 plus 10 plus 17, and we get 17 as our answer. So that's an estimation of a left-hand sum and as a right-hand sum. If you wanted a better estimation, you could use more rectangles or find an average. Now this is talking about upper sum and lower sum. So basically, you just have to know that you're going to have an upper sum and a lower sum, and depending on if the function is increasing or decreasing. So if the function is increasing, the lower sum would be the left-hand sum, because if you draw rectangles from the left endpoint, they go under. Whereas if you draw rectangles from the right endpoint, because it's an increasing function, those rectangles are going to be an over approximation or upper sum. If the function is decreasing, it's the opposite. The left hand is then going to be over. I'm using to draw a rectangle, I go up to the curve and I have to draw a rectangle over. And if it's decreasing and you're using right hand, then it actually ends up being an under approximation. So it kind of depends on if the function is increasing or decreasing, whether or not you have an upper sum or a lower sum. Okay, so what we're going to do now is spend some time, and we are doing a lot of work. Let's see if I can. I'm going to do a lot of algebra here. Okay. So find the upper and lower sums. Now they want me to do them in terms of n because they didn't give me a rectangle. Now I'm just going to preface, this part is a little tricky and kind of hard to understand. But just this one unit. So try your best and let's see if I can show you what I mean. So we're going to find the area in theory for given any number of rectangles. So we know that whenever we do this, we're always going to start with delta x, and delta x is b minus a divided by n. So 2 minus 0 divided by n. Now we don't have an n. Like in our previous problem, n was 4, so we knew it was 1/2. We don't have n, so we just have to leave it at n. Now, when we go to plug in our values, we have to figure out what are we going to plug in. And like to figure that out, if you remember earlier, I had 0 and I had 1/2 and 1 and 3/2 and 2. And so we plugged in, we added delta x to get what we plugged in. We plugged in f of 1/2. Then we added 2 delta x to get the second term, 1. Then we added 3 delta x to get the third term. Then we added 4 delta x to get this fourth term. So you're always adding delta x times the interval you're on. Delta x times I, because this was the first one, the second one, the third one, the fourth one, your interval. So 1/2 times 1 gives you 1. 1/2 times 2 gives you 1. I'm sorry, 1/2 times 1 gives you 1/2. 1/2 times 2 gives you 1. 1/2 times 3 is 3/2. And 1/2 times 4 gives you that 2. So our xi's, what we're going to be plugging in, is a plus delta x times I. A is the thing that you started with. So it's whatever you start with plus your delta x, in this case, it was 1/2 times your interval, gave us what we were plugging in. So we didn't have to worry about writing out i's for the example we just did because they told us that we knew our n was 4. So I didn't have to find it numerically with an expression that would work for any n. But this time we do. So a is your starting point. In this case, it's 0. Delta x is 2 over n, and we just write I. And now we're going to find f of xi. So we're going to take what we just wrote down, and we're going to substitute it into the function. So f of xi would be 9 minus 2 over n I squared. Or in this case, 9 minus 4 over n squared. Oops, I squared. Okay. Now we're going to do the summation. We're summing up those heights times delta x, because this is the height times the width. That gives you the area from I equals 1 to n. But again, we just have to leave it as n. So we're summing up f of xi is the 9 minus 4 over n squared, I squared times delta x, which is 2 over n. And then if I distribute that 2 over n to both of these, I get 18 over n minus 8 I squared over n cubed. And now what we're going to do here is we're going to bring the 18 over n out. So 18 over n, summation of 1, minus, I'm going to bring out 8 over n cubed, summation of I squared, and then we're going to substitute using our formulas we did from earlier. So when I sum up 1, I just get 1 times n. So it's 18 over n times n. And when I sum up I squared, that's when I get n times n plus 1 times 2n plus 1 over 6. Okay, definitely going to run out of room. Here, I'm going to come up here. So these n's cancel, and I can cancel one of these. So that'll be n squared. 8 divided by 2 is 4, and 6 divided by 2 is 3. So I have 18 minus 4 over 3n squared. And then if I multiply those n's out, n times 2n is 2n squared. And then plus n plus 2n, so plus 3n plus 1. And then if I do that, I can split this apart. So I can say 18 minus, let's go and multiply the 4n. So that'd be 8n squared. Oops. Over 3n squared minus, I'm going to distribute this 4 here. So 12n over 3n squared, and then minus 4 over 3n squared. And then I can simplify those cancel, and those would cancel with 1. So I have 18 minus 8/3 minus 12 divided by 3 is 4. So 4 over n minus 4 over 3n squared. And if you want to combine 18 minus 8/3, then that would give you 46/3 minus 8/3. Whoops, not minus 8/3. Whoops. That was combining. If I add these two together, I get 46/3. Minus 4 over n minus 4 over 3n squared. So this is a way to figure out the area underneath this curve for any n. So no matter how many rectangles I have, I could just plug in the number of rectangles and then I would get the area. Now it's having troubles. Let's see if I can save this before. All right, let's do the second part of this example here. So again, this is a little tedious, but we know that we have delta x is always b minus a divided by n. So we have 2 minus 0 divided by n, or 2 over n. Now we have the x of I, which remember we talked about, like if I'm at 0 and say my delta x was a half, then my right endpoint would be 0 plus 1/2. And then it would be 0 plus 2/2, which would end at 1. And then 0 plus 3/2. And then 0 plus 4/2, which would end at 2. That was if your delta x was a half, just to show you an example. So we're always adding delta x times whatever interval you're on. That would give you the right endpoints. But if we want to back it up to get the left endpoints, we need to do subtract 1. Okay, so the x of I are going to be your starting point, which is 0, plus delta x, which is 2 over n, times I minus 1. We got to back it up 1. So this would be 2 minus 2i minus 2 over n. And we're going to substitute that into our function for x to give us the summation. So we're trying to sum up from I equals 1 to n, f of xi, so it'd be 9 minus 2i minus 2 over n squared. That's f of xi, and then times delta x. Now we're going to try to very carefully multiply this out. So 9 minus 4i squared, and then you multiply these together, that'd be 4i, double it. So minus 8i, and then plus 2, and then over n squared. And then this is all being multiplied by 2 over n. At this point, I have 18 over n minus 8i squared over n cubed, if we multiply n squared times n. And then if I do a minus, that's going to be plus 8 times 2, whoops. 8 times 2 is 16 I over n cubed, and then minus 2 times 2, so minus 4 over n cubed. Just checking that's what I have written down here. 2 squared, oops, 2 squared is 4. Oops, 2 squared, 4. So 4 times 2, this should be 8 right here. Sorry, y'all. Okay, so I have 18 over n, and to make this a little bit simpler, I'm going to factor out 8 over n cubed from all of these guys. So I'm going to take out a negative 8 over n cubed. So that means I'd be left with I cubed here minus 2i over n, no, not over n, just 2i. And then here it would be plus 1. Okay, because I factor out a negative 8 over n cubed. Now we're summing up all of these things. So now we're going to break this apart. So we're summing up 18 over n. I'm going to bring the 18 over n out here actually and put 1. And then you're summing up, or that's a minus 8. We can bring 8 over n cubed out. And then we have I cubed minus 2i plus 1. So I cubed or I squared? I squared. I copied it wrong. All right, so now at this point, we can use the summation formulas that are on the previous example. So I'm going to substitute. When I am summing up C, if you remember when I'm summing up C, it's always C times N. Well, we just have N in general, so it's going to be 1 times N, which is N. So 18 over N times N gives us that 18. minus 8 over n cubed. Let's go ahead and substitute for each of these. So I squared, the formula is n times n plus 1 times 2n plus 1 over 6 minus 2 times I is n times n plus 1 over 2. So those 2's will cancel. And then plus, we're summing up 1. Again, you're summing up c n times, it's just 1 times the n, which I don't have my n written here, but that would be n. Okay, so if I go ahead and try to clean this up, 18 minus 8 over 6 would give me 4 over 3. So 4 over 3 n cubed or n squared. Could simplify that to be n squared because that would cancel with one of those. And then n plus 1 times 2n plus 1. And then I'm going to have a minus and a minus. So that's going to be plus 8 over n squared. N times n plus 1. And then minus 8 over n squared. Because this negative, we're multiplying this through. So we have a negative times a positive, and that n cubed cancels with that n to give us n squared. Okay, now we're going to very carefully multiply this in here. So that would be 4n plus 4 times 2n plus 1 over 3n squared. And then here we have plus 8n over n squared plus or 8n times n, that 8n squared over n squared, and then 8n over n squared. Oh no, this n cancels with that n. Whoops. Hold on, that n's not there. This would just be, let me fix that for a second. There's lots of room for error here. I'm sorry about that. Okay, so when I have this 8 over n cubed and I'm multiplying it here, this n cancels with that one to give us the n squared. So you're left with just 8 because the 2 over 2 canceled, so just 8 and then the n plus 1. So this would be 8n over n squared because I'm multiplying that 8n, and then plus 8 over n squared, and then minus 8 over n squared. So the 8 over n squared cancel, and this becomes 8 over n. And then when I multiply all of this out, I end up getting 18 minus 8n squared over 3n squared, and then minus 12n over 3n squared, and then minus 1 over 3n squared. And then this guy already separated, so plus 8 over n squared. And then if I try to clean that up, I notice that these cancel n squared over n squared, and that n cancels, so I have 18 minus 8/3. And then I have minus 12 over 3, so that's 4 over n, minus 1 over 3n squared, plus 8 over n. And then you can divide this 8 over n and this minus 4 over n to just have 4 over n. And the 18 minus the 8/3 simplifies to 46 over 3. So that's that. It's very long and tedious. I hope that that makes a little bit of sense, but again, this is more so to show you the theory of what we're doing whenever we're finding the integral of something. Okay, so now this says we're going to use the limit process to find the area under the curve of 3x minus 2 from 2 to 5. First, let me just draw a picture of this so you can kind of understand what we're doing. 3x minus 2, 1, 2, and then from 2 to 5, here's 1, 2, 3, 4, 5. Let's see, what would the x-intercept be? If I let y be 0, I get x equals 2/3. So we got down 2 and then up 3 over 1. So 2/3 is our x-intercept. So we have a line going up like this, and it would be a triangle, right? We're going, or actually a trapezoid, because we're starting at 2 and ending at 5. 2, 3, 4, 5. So we're trying to find the area, which you could totally find geometrically. You're trying to find the area from 2 to 5 underneath this line. Okay, so let's see now. I could do that by actually using trapezoid formula, but what we're trying to explain is we're cutting into rectangles. So you're having a rectangle, and the more rectangles you have, the more accurate of an estimation you would have. You're either going to have an overestimation if you do the right end, or you're going to have an underestimation if you do the left end. So we're trying to find the area underneath this curve, and we're going to use it, use the formula, the limit process. So we're going to take the limit as delta x goes to infinity. Okay, so you want to have, or sorry, delta x goes to 0, which is the number of n rectangles going to infinity. Okay, so that's delta x, the change in x going to 0, or n going to infinity, because you want to have an infinite number of rectangles. So you're cutting this up smaller and smaller and smaller and smaller until it would be, in theory, the perfect area. So we're going to find our xi, our delta x, like always. Our delta x is b minus a divided by n. So 5 minus 2 divided by n, so it is 3 over n. Then you find your xi. Your x of I is always a plus delta x times your I. So a is this first guy, your first place you're starting, which in this case is 2. Your delta x is 3 over n, and then we have times I. So this is what you're plugging in to your function, to your f of x. So we're going to take this guy and we're going to substitute him into f of x. If I do that, f of x, plug this in for x, I get 3 times 2 plus 3 over n, I minus 2. So that would be 6 plus 9 over n, I, and then minus 2. So we have 6 minus 2, that is 4 plus 9 over n, I. So hopefully kind of makes sense so far. So now what are we going to do? We're going to take this and we're going to do our limit process, which we're finding the summation of f of xi. Oops, let me change from I equals 1 to n, and it's f of xi times delta x, because these are rectangles. It's delta x is the width times f of xi, which is the height. That gives you the area of one rectangle, and you want to have an infinite number of rectangles, and you're summing them all up. So f of xi is 4 plus 9 over n I, and then we have to multiply it by delta x, which again, delta x is this 3 over n. And we're summing it up from I equals 1 to n. So if I distribute this, I get 12 over n plus 27 over n squared times I. Summing this up. So now I can split it apart, and I can say it's the summation of 12 over n plus 27. I'm going to go ahead and bring over that n squared. We can bring the 12 over n out here. So 12 over n, make that a 1 right here so you can see it. And we have I equals 1 to n, and we're going to let n go to infinity. So we know when we sum up 1 n times, it just says n times 1. So 12 over n times n gives us 12. Plus 27 over n squared, I is n times n plus 1 divided by 2. So this will cancel with one of those. And so then at this point, if I want to distribute, I have 12 plus 27 over n times n. So that is going to cancel. We're going to get 27 over 2. Whoops. And then 27 over n times this 1. So we get 27 over 2n. Then we let n go to infinity. If I let n go to infinity, I don't see an n here. I don't see an n here. I only see an n here, and it's on the bottom. So this is going to go to 0 because the bottom is getting huge. So I'm left with 12 plus 27 over 2. And 12 plus 27 over 2 gives us 25.5. That is the area of this trapezoid under the line from 3x minus 2 from 2 to 5. And this is going to be the definite integral. This is also known as the integral from 2 to 5 of 3x minus 2 times dx for delta x. That is what this is equal to, 25.5. So that is a long example kind of proving the area. Now, I'm going to skip the midpoint, or actually no, okay. I don't like how they wrote it here. I feel like that looks confusing. I'm going to show you how I think about the midpoint rule, just using kind of common sense. So this tells us our n is 4. In all of these problems, you always start with delta x is b minus a divided by n. It's helpful when they give you an actual n, like in this case, 4. So b minus a, that's this endpoint minus that. So pi over 2 minus 0 over n is 4. So that is pi over 8. This tells you what you count by. It's your width of your rectangles. I always draw a little number line with where I'm starting, 0, and then where I'm ending, and I count by whatever my delta x is. So I count by pi over 8. So here's 1 pi over 8. If I say 2 pi over 8, that would be pi over 4. And then 3 pi over 8 here, and then 4 pi over 8 would be here. And then I go back and count, do I have four ends, 4 subintervals? 1, 2, 3, 4. Yes, I do. That means that we did this correctly. Now, what is my delta x of each of these rectangles? My width is pi over 8. So I can pull that out front because that's a common width. And then I just need to get 4 heights, because there would be 4 rectangles. Now, we can either get the left one, or we can get the right one, or in this case, we can get the middle one. And instead, that gives us a better estimation. So I can go back and look at the middle of each of these guys to figure out what I'm going to plug into this function, how I'm going to get my y values. So what's between 0 and pi over 8? That would be pi over 16. Between pi over 8 and pi over 4, that's 3 pi over 16. Between pi over 4 and 3 pi over 8, that's 5 pi over 16. And then here, that is 7 pi over 16. And we're plugging all of these into cosine. So it would be cosine of pi over 16, and then cosine of 3 pi over 16, and then cosine of 5 pi over 16, and cosine of 7 pi over 16. We evaluate them, and when we do that, we get 1.006. That's an approximation of the area under cosine from 0 to pi over 2 using the midpoint rule. So instead of using the left endpoint or the right endpoint, you use the one in the middle. Okay, attempt your assignment, and again, please let me know if you have any questions.